Arratsalde on guztioi eta ongi etorriak Claude Cohen-Tannoudji jaunaren hitzaldira. Es para mí un gran placer presentar a Claude Cohen-Tannoudji y escuchar una vez más una de sus conferencias. Si bien sabemos que la invención de los láseres fue la fuente de una revolución tecnológica, hay que destacar que creó también una revolución en la ciencia. Por supuesto, el láser permitió el desarrollo de técnicas experimentales inéditas, pero además el láser por sí mismo ha revolucionado el estudio de la interacción entre la materia y la luz, los fotones en el lenguaje de la mecánica cuántica. Claude es un científico emblemático en este último campo de investigación, tanto por su capacidad de diseñar experimentos de punta como por elaborar tantos conceptos novedosos que no trataré de inventariarlos. Me limitaré con mencionar dos de ellos que llevan nombres tan impactantes como el enfriamiento sísifo o el famoso concepto de átomos vestidos de fotones. Además de sus logros en investigación, Claude destaca como docente por su capacidad excepcional a la hora de transmitir a sus estudiantes o colegas no solo los resultados de su trabajo, sino también un método de pensar que permite luego pensar por uno mismo. Por ejemplo, a través de sus cursos y libros, generaciones de físicos han aprendido a pensar cuánticamente. Me parece oportuno relacionar lo que acabo de decir con una frase que aparece en su autobiografía en la Fundación Nobel. Claude subraya que recibió de su padre, un autodidacta, lo que él considera como lo más hondo de la tradición judía: estudiar, aprender y compartir conocimientos con los demás. Diciendo esto, nos transmite el mensaje de que la ciencia es una actividad humana y como tal moviliza toda la cultura y la educación y no solo el dominio de técnicas especializadas. Por extensión del concepto fotónico, yo diré que el científico vive y trabaja vestido de colegas, colaboradores, familiares y amigos. Eso Claude lo hizo manifiesto en su práctica profesional. No quiero retrasar mucho más el placer de escuchar a Claude. Muy a menudo he escuchado charlas o he seguido cursos de colegas sobre temas que me parecían muy difíciles de entender, aunque el locutor dijera que era muy sencillo. Así que al final me sentía un burro. Con Claude ocurre lo opuesto. Por respecto a la audiencia, dedica tal empeño en presentar las cosas con rigor y claridad que uno las recibe como una revelación y al final se tiene la sensación de ser más listo. Gracias, Claude, por haber venido y por hablarnos sobre el tema utilizando la luz para manipular átomos.
Thank you, Antoine, for your very kind introduction. Thank you very much, Pedro, for inviting me to this wonderful conference full of passion. You know, we are celebrating today the 10th anniversary of the DIPC. In fact, 2010 is also 3 other anniversaries. It's the 60th anniversary of optical pumping. The original paper of Alfred Kassler giving the idea of optical pumping dates 1950. It's also the 50th anniversary of the realization of the first laser by Ted Myman. And also, it's the 15th anniversary of the first gaseous Bose-Einstein condensate, which is a very great issue in atomic physics. What I would like to do in this lecture is to describe a few advances in atomic and molecular physics realized by using light for manipulating atoms. And I would like to try to point out a few trends and a few perspectives of this research field. You know, I will deal in all my lectures with light and matter. Understanding light and matter, how they interact, has been always the central question in physics. It has been at the origin of conceptual and technological revolution, like the relativity theory, like quantum mechanics, like the light, which is a completely new type of light. You know, when you look at the light emitted by atoms, you get information on these atoms in the medium where they are located. That's the purpose of spectroscopy. But a new point of view has been developed during the last few years, the last few decades, is to use light for manipulating atoms, for changing their properties. And I would like to describe in this lecture how can one polarize atoms with light, how can one cool them to extremely low temperature, what are the new research fields, what are the new applications which have been opened by this research. That's the central theme of this lecture. Before starting, let me just remind you the basic interaction processes between atoms and light. They consist of emission and absorption. We know that the energy levels of an atom are quantized, they are discrete. And an emission process is a process where an atom goes from an upper state to a lower state. It loses energy by emitting a light quantum, which is called a photon, with an energy h nu, where h is the Planck constant, and nu the frequency of the light associated with the photon. And of course, you have the reverse process, which is called the absorption, where an atom in the lower state, A, can go to upper state by absorbing the energy given by a photon, h nu. And of course, energy conservation implies that the difference between these two energies is equal to the energy of the photon which is emitted or absorbed. And this equation shows you that if with the spectrometer you measure the frequency of the light which is emitted or absorbed, you can determine the energy difference between two levels. And you can reconstruct the energy diagram of the atom. This is the principle of spectroscopy. Light is a source of information on the structure of atoms and a probe for detecting their presence in a medium. And during the last few decades, spectroscopy has been developed tremendously in all frequency range, from the radio frequency to the gamma ray, with a lot of improvement. Let me just give you an example of spectra of 3 different atoms: hydrogen, mercury, neon. You see clearly that the spectra are not the same, because the energy levels are not the same. So by looking at the spectrum of the light emitted by a medium, you can identify what are the atoms which are in this medium. It's some sort of a fingerprint or genetic signature. Also, when you look at the light coming from the universe, when I call light, I mean electromagnetic radiation in all frequency range, you get information on the structure of the universe. And I like very much this picture, which has been taken by a satellite looking at the microwave background radiation, which is some sort of a remnant, a fossil of the light which escaped from the bith medium following a few hundred years after the Big Bang. And you see this light, this microwave radiation gives you a picture of the distribution of matter 13.7 billion years ago. And we have these inhomogeneities under the influence of the gravitation that will give rise to the galaxy. So that, I think, is a moving picture, because that gives you what the universe was looking like 13.7 billion years ago. So you see that all the understanding of the universe in which we live come from the observation of the radiation we receive from the star and from the galaxy. But there is another way of looking at light. Light is also a tool for manipulating atoms. Because when an atom absorbs a photon, it acquires certain properties of this photon, its energy, its angular momentum, its linear momentum, and by choosing conveniently the light beam which excites the atom, you can change the property of the atom. And I would like to illustrate this idea with two examples. First one, how you can change the spin, the polarization of the atom by exciting this atom with polarized light. That is called optical pumping. And that allows you to detect magnetic resonance, which was mentioned in the early lecture 2 days ago, in very dilute medium, not in a liquid or in a solid, but in a gas. Second example, I will show you how when you absorb light coming from a given direction, you can exert on atoms a force, which is called a radiation pressure force, which changes the velocity of the atom and which allows you to get ultra-cold atoms at extremely low temperature. So let me start with the idea of polarizing atoms, which is called optical pumping, how you can transfer angular momentum from polarized photon to atoms, and how you can polarize atoms. And as I mentioned to you at the beginning of my lecture, in June of 1950, that was the original paper by Alfred Kessler, who is here, with his closest collaborator, Jean Brossel, who was proposing to use polarized light for producing differences of population between Zeeman sublevels of atoms. The word optical pumping was not yet coined at that time. You know, Kessler was a very great man. He was not only a scientist, he was also a poet. He was looking at science like a form of art, and he was doing very elegant way. So the idea is the following. When you took a sample at usual temperature, at room temperature, and in weak magnetic field, you can demonstrate statistical mechanics shows you that the spin states of the atom are equally populated. By spin state, I mean that when you have, for example, a spin 1/2, quantization of angular momentum implies that the atom can exist only with a spin up or spin down. The angular momentum is quantized. It's like a spinning top, which can be either spinning in that direction or in that direction. And the difference of energy between the two spin states is so small that Boltzmann factor, which expresses the thermal equilibrium, implies that the two spin states are nearly equally populated. You have a small difference of population. But when you do magnetic resonance on such a system, by flipping the spin from the spin up to spin down, you can show that the signal is proportional to the difference of population between the two spin states, to the absolute value of the difference of population. Since the polarization is very weak, the absolute value of the difference is only large when you have many, many atoms. So this is why magnetic resonance is usually detected in liquids or solids, where you have many, many atoms. In gases, it's much more difficult. The idea of Kessler was very simple. When you took polarized light, like, for example, with the polarizer such one you have in your sunglasses, you can show that polarized light, the photons associated with polarized light, has an angular momentum. And it's very easy to polarize light by using polarizers. And when an atom absorbs polarized light, it gains the angular momentum of the photon, and it becomes polarized. So that's the idea of optical pumping, and then you can get gaseous samples, very small number of atoms, with a very large spin polarization and with the difference of population between the two spin states, which is large enough to obtain magnetic resonance signal. And we can make magnetic resonance available in gaseous samples where atom-atom interactions are weak, where the perturbation due to collision is not large enough. So, the important features of this technique, which has given a lot of application, is that you can get high degree of spin polarization by light, and in fact that was, I think, the first example of manipulation of atoms by light, by polarized light. It led to a very sensitive optical detection of magnetic resonance in dilute atomic vapors. It provided high resolution radio frequency and microwave spectroscopy, and it allowed the discovery of many important effects which were not observed before, like what is called multiphoton processes, where an atom goes from one state to the other by absorbing not a single photon, but 2 or 3 or 4. And these multiphoton processes were first observed in the RF domain by optical pumping experiment, and now they play a very important role in physics, in laser physics, by what is called, for example, high harmonic generation, which allows you to make very short pulses of light. It allowed also the discovery of an effect which I will describe in detail afterwards. It's the possibility that light displaces the energy level. It's called light shift. And we will see that this effect, which was discovered in the early days of optical pumping, plays a very important role now in laser cooling. It also introduced a very important idea in physics that when you have an ensemble of atoms, you cannot describe them just by giving the probability of occupation of the different energy levels, the so-called population. You have also some linear superposition of states, which are very important in physics, because in quantum mechanics you have this idea of linear superposition of states. And that a lot of applications. Let me just mention one of them. If you prepare an excited atom in a linear superposition of two states by a short pulse of light, then when it decays by emitting light, since the two levels have been created in a coherent way, the two light waves coming from the two levels beat, and you get what is called quantum beat. Exactly what you do when you hit two piano strings, then you hear the beat note between the two piano sound waves coming from the piano. And also a lot of practical application, magnetometers, atomic clocks, magnetic resonance imaging. And I would like to discuss one or two of these things. First, the light shift. The point is the following: if the light which excites the atom is slightly off resonance, not exactly on resonance, but slightly off resonance, you can show that the light displaces the ground state, which is represented here. The ground state G is displaced if the light is detuned to the blue, if the frequency of the light is larger than the frequency of the atomic transition, the shift is positive. If it is lower, the shift is negative. So the shift has the same sign as the detuning between the light and the atomic frequency. And the shift is proportional to the light intensity. If you double the light intensity, you double the shift. Also, you know, in fact that was my PhD work in 1961. I was studying both theoretically and experimentally the light shift effect. And there are two ways of considering this effect. First, it's a perturbation, because the light that you are using in the experiment change the energy level and change the atomic frequency you want to measure. And for example, Ted Hensch described yesterday the high resolution spectroscopy of hydrogen with two-photon spectroscopy. You have to correct the measurement by the light shift. You have to extrapolate the measurement to zero light intensity to extract the correct frequency. But what is amusing is that 30 years after, you can now consider this effect in a positive way. since you can change the energy levels, you can use this effect for manipulating the internal state of an atom. You can change the energy either in the positive way or the negative way, and we will see example of application. Let me also describe you a practical application of optical pumping, which was completely unexpected some years ago when Kastler did his work with his students and his colleagues, and the idea came afterwards. This is very often a practical application is not planned in advance. It appears after the discovery. Okay, you see, suppose that you polarize a gas of helium. Helium is a rare gas. It does not hurt the body. It does not react with the body. Helium-3, the isotope 3 of helium, has a nuclear spin. Usually, the polarization of nuclear helium is very weak. But if you polarize helium-3 by optical pumping, you can achieve very high degree of polarization. Now, if a patient breathes a mixture of air and helium-3, the lungs are filled with the polarized gas. And then you can make magnetic resonance imaging of the cavity of the lung. Usually, magnetic resonance imaging is done by using the magnetic resonance of the protons, of the hydrogen atom, of the water molecules, which are contained in the blood, in the flesh, in the bone. So what you see in MRI is the flesh or the blood or the bone. You don't see the empty part of the body. And this is, for example, a proton image of the chest of a patient. You see the coast, the stomach, the earth, but you don't see the lung. But if this patient breathes in polarized helium-3, then you can make an MRI image of the cavity of the lung. That shows you how a practical application can come after a basic discovery. And a few more pictures of that. That's a healthy lung. That's a lung of people having asthma and a heavy smoker. So you see that this technique now is a very important technique for diagnosis of the cavity of the lung. Now I take the second example. How can you change the velocity of an atom by light? And let me take first, remind you what is important, that these experiments have been made possible with the second anniversary, which I mentioned, the realization of lasers. The idea of lasers were put forward in 1958 by Charlie Towns and Art Shallow, and the first realization was done by Theodor Maiman in 1960, 50 years ago. And you know, these light sources, at the beginning, really nobody was believing that was very important. I remember I was a young student in 1963, attending a meeting in Paris, one of the first meetings where people were reporting what was happening with lasers, and most people, including scientists, were considering that, okay, that's a good idea, that will never get out of the lab, that's a toy for physicists. They will never have a practical use. But it was completely wrong. You know, lasers have introduced a revolution both in basic science and in application. Now the market of lasers is several billions of dollars. Let me focus here on the fundamental physics. You know, lasers have dramatically changed the situation in high-resolution spectroscopy. We had yesterday in the Ted Hans lecture beautiful example of how the progress of high-resolution spectroscopy has been spectacular. Nonlinear optics, quantum optics, where you have nonlinear effect with light. Fundamental test. We have heard yesterday about this recent experiment on the radius of the proton, which was available with the use of laser light for measuring the lump shape of muonic atoms, which is a very good surprise, which nobody knows if it will be some explanation of this result. Also, let me remind you or tell you that one of the great achievements of atomic physics has been the discovery of the fact that left and right are not equivalent for atoms. Parity is violated in atomic physics. If you take an experiment which obeys the law of physics. And if you consider the mirror image of this experiment through a mirror, the image does not obey the law of physics. Physics is not invariant in a reflection with respect to a mirror. That was done, suggested and done for the first time by one of my colleagues in the Kessler group, Marie-Anne Bouchia, in 1982, and then improved significantly by Carl Weyman in Boulder. Also, intense laser field effect, multi-photon ionization of atoms, high harmonic generation. The spectacular application of laser now is the generation of ultra-short laser pulses, femtosecond, a million of a billionth of a second. It's so short that you can look at the vibration of a molecule in real time, what is called femtochemistry, and now the progress in this field, and there are so many nice experiments in the DIPC. Now the attosecond regime is reached a billionth of a second, ultra short pulse, where you can now have access to the motion of an electron in an atomic system. And also, I will now focus on this, the control of atomic motion by laser light, how you can change the velocity of atoms and trap them in very small space. And also a very, very promising field, how you can use the quantum properties of atoms for transmitting, for processing information, which is the field of quantum information. Okay, I will not, since Ted has mentioned the experiment on the radius proton, I will skip this slide, and I will go directly now to the force exerted by light on atoms. And to give a simple picture of what is happening, I will take a very simple example. Suppose that you have a target, C, here, which is bombarded by a beam of projectiles, P, coming all from the same direction. The projectiles bounce on the target in all directions, and as a result of the bombardment, the target is pushed. I'm sure that you have one day worked in a very heavy rain coming in front of you, and then you are slowed down by the rain. In more sophisticated terms, you can see that the transfer of linear momentum from the projectile to the target gives rise to a force. The same picture can be given to you replace the target C by an atom, and you replace the projectiles P by photons, which are absorbed by the atom and remitted in a random direction. So it's the same situation, and as a result of that, the atom will be pushed because it absorbs and remits photons. It is bombarded by photons, and in fact, this effect appears already in astrophysics. When you look at the tail of the comet, a comet is an astrophysical object surrounded by some dust, and the light coming from the sun, the comet is orbiting around the sun, and the light coming from the sun pushes the dust and gives rise to the tail of the comet. This is part of the explanation. There are also other processes. And the tail of the comet is along the direction of the sun and not on the tangent of the trajectory. And if you use now laser beam, even with moderate power, you can demonstrate, I will not bother you with that, you can show that the acceleration or the deceleration, the force exerted by laser light on atoms can be very huge. And it can communicate to atoms an acceleration or deceleration which is 100,000 times bigger than the acceleration due to gravity. Which means that if you start with an atom moving with 1 kilometer per second velocity, you can stop it in a distance of 1 meter. So this gives you an idea of how big is the force. Now, using this force, you can slow down and cool atoms. Slowing and cooling are two different concepts. If you have an ensemble of atoms, it is described by a velocity distribution, which gives you the distribution of all possible velocities of the sample. And this distribution has a mean value and has a certain dispersion spread around the mean value. Slowing down mean reducing the mean value of the velocity, but that's not the temperature. In physics, the temperature is not it's a concept which is not related to the mean value of the velocity. It is the velocity spread around the mean value. It characterizes the disordered motion of an atomic sample. And by laser light, you can reduce this velocity spread, that is to say, you can reduce the temperature. And that's cooling. And in this picture, you have a ball of sodium atoms at the intersect of 6 laser beams, 2 along X, 2 along Y, and 2 along Z. And you see this cloud of sodium atoms is cooled at a temperature which can be on the order of 1 or 2 microkelvin, 10 to the minus 6 Kelvin. You know, in physics, one uses in general the Kelvin scale, which is not the Celsius or the Fahrenheit scale. For example, the room here, if you have 27 degrees Celsius, it is 300 Kelvin. So, with laser cooling, we can cool atoms to 10 to the minus 6 Kelvin. Much, much smaller. And to give you an idea, the velocity of the atoms which are cooled are on the order of a few millimeters per second, whereas the molecules of hydrogen, of oxygen and nitrogen in the air around us is on a few hundred meters per second. So, you know, the atoms are very quiet. Okay. And, now let me give you a few examples of cooling mechanism. Let me start with the simplest one, using the Doppler effect, which is called Doppler cooling, and which was first suggested by Ted Hunt and Archalo, Dave Wineland and Hans Demels in the middle of the 1970s, and which is very simple and beautiful idea. What you do, you use now 2 laser beams, counter-propagating, with the same intensity and with the same frequency. New light, new laser, they tune slightly below the atomic frequency, new atomic. What happens? If you consider an atom between these 2 waves, if it is at rest, there is no Doppler effect. The 2 forces are equal and opposite, they cancel out. So the total force is equal to 0. If the atom is moving to the right, because of the Doppler effect, the wave coming in the opposite direction will have its frequency shifted up. When you have a train coming in front of you and you are moving towards the train, if you have a sound, it looks higher frequency, that's the Doppler effect. So mu L will be shifted up, it will get closer to resonance, more photons will be absorbed, and the force will increase. And the conclusion are reversed here. The Doppler effect will be negative, mu L will be shifted down, farther from resonance, less photons are absorbed, and the force will decrease. So as a result of the Doppler effect, the 2 forces no longer balance, and you get a net force opposite to the velocity, and which for low velocity is linear in velocity. This is what is called a viscous medium. When you are trying to move a spoon in a pot of honey, the faster you move, the bigger the resistance. That's the viscosity. This is why people call that effect optical molasses. It's like the molasses where the honey is replaced by light. Okay, but when at the end of the 1980s, people started to measure the temperature very precisely, the temperature that they observed was about 100 times lower than the temperature which was predicted for the theory of Doppler cooling. Usually, when you do an experiment, it works less good than predicted by theory. Here it was reversed. It was 100 times better than theory. That means that Doppler cooling is not the only mechanism, and this is where, in our lab, the experience we had on optical pumping and light shift was useful because we identified what was happening with my young colleague, Jean Dalibard, in Paris. And this is what we call Sisyphus cooling for the following reason. You know, in the explanation I've given for cooling, we have took a very simple ground state. without structure. In fact, alkali atoms have a Zeeman structure. They have different spin states. Suppose, for simplify, I take only two spin states, spin up and spin down. Two spin states, two sublevels in the ground state. When the two laser beams are coherent, they give rise to a standing wave with nodes, zero intensity, and antinodes, maximum of intensity, node, antinode. You get a standing wave with a periodicity of intensity given by the half of the wavelength of light. Since in laser cooling the light is detuned from resonance, we will have a light shift. The two levels will be light shifted. And they will be shifted by different amount because of the polarization of the light. So one level will be shifted like that in space, and the other one will be shifted also periodically. And also, the light is not too far from resonance, so the atom can absorb light from one level and come back to the other level. You can have optical pumping between the two spin states. And you can achieve a situation, which is the following one, where the atom moving to the right starts from the bottom of a valley, climbs a potential hill, and when it reaches the top of the hill, it has a large probability to be optically pumped in the other states, which is the bottom of the valley, and so on. So you see that it is exactly in the situation of the hero of the Greek mythology, Sisyphus, who was condemned to roll up a rock at the top of a mountain, and when he was at the top, God was putting the rock at the bottom of the valley, and they had to do the job again and again, and that's exhausting for the guy, and that's also exhausting for the atom, that slows down the atom, and you can make the theory of this effect and show that it explains what you observe. And with this mechanism, you can reach the microkelvin range. We have also developed other mechanisms which I have no time to explain. Let me just end this review of the mechanism with one mechanism which is very simple to understand, which is evaporation. But it is common in real life. Suppose that you have a potential well, like that, with a depth U0, where you have trapped atoms. And consider two atoms with energy E1 and E2, and suppose that the density is high enough to have elastic collision. So the two atoms collide, and after the collision, they have energy E3 and E4. And because of the conservation of energy, E1 plus E2 is equal to E3 plus E4. If E4 is larger than the potential depth, the atom with E4 will leave the trap. It will evaporate. The remaining atom will have a much lower energy, E3, and by colliding with the other atom, by thermalization, the whole sample will cool down. You lose atoms by evaporation, but those which remain in the trap are cooler. This is exactly what you do when you blow your cup of coffee. You evacuate the hot molecule, and the coffee cools down. And when you start from a laser-cooled sample at high enough spatial density, and when this process takes place, you can reach the nanokelvin range, 10 to the minus 9 Kelvin. So you can also trap atoms. And let me give you another application of light shift. Suppose that you take a light beam, a laser beam, and you focus it tightly. And suppose that the light beam is detuned to the red. So the light shift of the ground state is negative. So when you cross the focus of the beam, you see that the ground state energy is shifted down. You have some sort of potential well. The laser beam creates a potential well in which you can trap atoms if they are cold enough. And that's called laser traps or optical tweezers. They can be used also to trap biological objects like bacteria or viruses. Also, if you take not a single beam, but several beams to make a standing wave, and if you detune from resonance, you will have a periodic array of potential wells in which you can cool atoms, you can trap atoms if they are cold enough. And you know, such a structure is quite similar to a box for eggs. You know, of course, a box for eggs, and the eggs are trapped in the potential well, and you can do the same thing with atoms, and that's very interesting now. And I used a lot of laboratories because the motion of an atom in such a structure, which is called optical lattice, and which were, for example, studied in the beginning in our lab by Gilbert Grimbert, who unfortunately died at a very young age. You get an optical lattice. The motion of an atom in optical lattice is quite similar to a motion of an electron in an ionic crystal. So you get a structure, a new structure, with completely different orders of magnitude, which reminds structure found in condensed matter, in solid-state physics. But the important point is that these optical lattices are very flexible. You can do with them things you cannot do with a crystal. You can switch off the laser beam. You cannot switch off the periodic potential created by the ions in a crystal. You can change the intensity of the light. You can change the depth of the well. And you can change the tunneling of the atom between adjacent potential wells. So you have a possibility to manipulate the tunneling effect between potential wells. Okay. So perhaps to summarize all these techniques, I've represented here a temperature scale in Kelvin units to show you what has been achieved. The interior of the sun is several million Kelvin. The surface of the sun is several thousand Kelvin. The Earth, I mentioned 300 Kelvin. The cosmic microwave background radiation, the remnant of the Big Bang, is 2.7 Kelvin. By cryogenic technique, liquid helium, dilution of the refrigerator, you can use, Vilsek showed us yesterday the big tunnel in LIC full of liquid helium at 2 degrees Kelvin, that cryogenic technique. And you see with laser cooling, CC cooling, evaporation, you reach now the scale of microkelvin, nanokelvin. You can see that what we have now in the laboratory is the coldest matter in the universe. Really very cold and very dilute. Now, what can you do? Once you have achieved this cold atom, what can you do with them? What are the possible applications of these ultra-cold atoms? In fact, there are two great categories. Since cold atoms are moving slowly, you can observe them for a long time, much longer than when you have an atom passing in front of you at 100 meters per second. And in physics, the time-energy uncertainty relation tells you, in quantum mechanics, that the longer you observe a system, the more precise the measurement you can perform on this system. So with cold atoms, you can increase dramatically the precision of the measurement, and you can make, for example, much more precise atomic clocks, which improves, of course, the GPS system, which we all know now. Now, a second great category of experiment, of application, is the fact that, as shown first by Louis de Broglie in 1924, with any matter particle is associated a wave, which is called the de Broglie wave. And the wavelength, lambda de Broglie, of this wave is given by a simple formula, h, the Planck constant, divided by the product of the mass of the particle and the velocity. And you see, the de Broglie wavelength is inversely proportional to the velocity. If you decrease v, you increase lambda de Broglie. At room temperature, the de Broglie wavelength of atoms is below nanometer. It's extremely small. So the wave aspect of atoms at room temperature is completely negligible. But at nanokelvin, it can be 30, 50 microns, so it becomes macroscopic. So the wave nature of atoms becomes much easier to observe and to use. And with that, you can repeat with de Broglie waves all the experiments well known with optical waves. You can make Young fringe, atomic interferometry. You can make gyrometers, radiometers using matter waves. And you can also achieve new states of matter, which are called ultra-cold quantum gases, like Bose-Einstein condensate, Fermi gases, and a lot of fascinating new states of matter. So let me first describe this application. And let me first tell you how we can measure what is an atomic clock. What does it mean, an atomic clock? You know, a clock is an oscillator which has a periodic motion, for example, a quartz. But if you take two different quartz, they oscillate in general at two different frequencies, and if you take even a single quartz, each frequency will change in time. It will drift. What you want to do is to have an oscillator whose frequency remains the same, and which is the same everywhere, here, in New York, in Moscow, in Paris, everywhere. So what you do, you take an oscillator, and you generate a wave, and you scan a transition frequency between two atoms, between two levels of an atom. In fact, the definition of the second, international definition, is based on a certain transition of the cesium atom. So you scan the resonance, which is centered at the atomic frequency, omega A, with a certain width, delta omega, and with the servo loop, you lock the frequency of the oscillator to remain always on the center of the atomic line. So now the oscillator is no longer allowed to move as it wants, it's always obliged to remain centered at the atomic frequency. That's the principle of an atomic clock. But when you look at this picture, it is clear that the narrower the transition, the smaller delta omega, the better will be the locking. To have a good locking, it's nice to have a very narrow line. But as I mentioned to you, delta omega, the width, is inversely proportional to the observation time. So if you increase the observation time by factor 100, you decrease the width by 100, and you have a clock which is 100 times more precise. This is why ultra-cold atoms are very useful for having very precise clock. Up to now, the usual clocks, which were in all metrological laboratories, were using cesium atomic beams, moving with a velocity of 100 meters per second. The type of atomic beam that Dudley explained yesterday in his lecture. And this beam of cesium atom passes through two microwave cavities fed by the same microwave source and separated by a distance of 50 centimeters order of magnitude. And you can show, that was the theory of what is called Ramsey fringes, the device invented by Norman Ramsey. If you have an atomic system and they're going two perturbations, the first one here, the second one here, coherent, you get fringes in the transition probability whose width is determined by the time of light, the separation of time between the two perturbations. So the observation time here is the time it takes for the atom for going from this cavity to this cavity. 0.5 meter with a 100 meter per second velocity gives you 5 milliseconds. So the observation time in usual clock is in the millisecond range. What you do now with cold atoms? Of course you could take slow atoms, but if the atom is too slow, they will fall in the gravity field. So instead of that, you throw up the atom and you make what is called a fountain. You take a ball of cold atoms, and with the laser pulse, you throw these atoms up, they go up and down, and they pass through the same microwave cavity, once on the way up and once on the way down. And now the time separating the two interactions with the microwave field in the cavity is the time it takes for going from here to here. If the height of the fountain is h, the high school formula gives you the time separating these two interactions, and is given by this equation, where h is the height of the fountain and g is the gravity due acceleration. And if you take h equals 30 centimeters, you find 0.5 seconds, 500 milliseconds. So you gain a factor 100 in the observation time. So you see, this is called a fountain because it really looks like a fountain of water, except that you replace the water molecules by the drop of water by atoms. And fountains have been achieved by several groups, on sodium by the group of Steve Chu in Stanford, on cesium by a group of Christophe Salomon and André Clairon, who was here at the Observatoire de Paris, and Ted Hans mentioned yesterday the fountain, the transportable fountain they have that they used in Munich for doing some precise measurement. And that gives you an example of the Ramsey fringes observed by this fountain. And let me give you the performances. The relative accuracy of this clock range in the 10 to the minus 16 range. What does that mean? That means that if you have a stability of 10 minus 16, means that if you have a clock starting now, 300 million years after, it will be off by less than 1 second. So it keeps the time for 300 million years for better than 1 second. Of course, these clocks are very useful for improving the GPS system. In physics, every time you need to measure frequency, you need clocks. You need frequency comps for measuring frequency, and all the metrological applications are based on clocks. And in fact, physicists are never happy. They want always to improve. You are always bothered by gravity. So how to get rid of gravity to go to space? And to go to space, first you can try to do the experiment in microgravity. Microgravity is the following thing. You have jets, Airbus or Caravelle or Boeing. The pilot put the flight in ascending zone, and switch off the engine, so the flight make a free fall, parabola. And of course, before it crashes, switch the engine again, and you have a second parabola. Each parabola lasts about 20 seconds, and in the plane you have about 20 groups, physics, chemistry, biology, industry, metallurgy, doing microgravity experiment, and that shows you the cold atom groups, not me because I'm too old for doing this kind of sport, and trying to make the clock operating in this microgravity environment, and in this case you can gain a factor 10 more. You gain a factor 1,000 compared to the microwave clock on Earth. And of course now it's planned to put a cold atom clock in the space station in 2013 with the hydrogen measure. So we'll have in the space station ultra precise clock delivering time to all clocks on Earth and to all clocks of the satellite system, synchronizing all these clocks, and also allowing to do fundamental tests of physics, in particular of general relativity, the redshift, Einstein redshift. Einstein predicted that if you have two clocks in two different potentials, gravitational potential, the frequency of the clock are not the same, and the relative difference, delta omega over omega, is equal to delta U divided by c squared. By comparing the frequency of the clock in the space station to the frequency of the clock in the ground, we hope to be able to test redshift of Einstein with an accuracy about 30 times better than all previous tests. In fact, in parallel with the development of microwave clock, there are a lot of effort devoted to optical clock using not a microwave transition, as it is the case for the cesium atom, but an optical transition. They are more difficult to achieve, but spectacular progress has been realized during the last few decades. And I show you here the progress of the cesium clocks, here, about a factor 10 every 10 years, and the progress of the optical clocks with the comps, and you see now the optical clocks are better. More difficult to achieve, I see we'll have to wait one or two decades before being able to put them in space, but they reach now a stability of 3 × 10⁻⁷, which corresponds to an error smaller than 1 second in 1 billion years. And to a sensitivity, if you have two clocks at a difference of altitude of 30 centimeters, you can detect them. And in fact, even more, the more recent reported accuracy for aluminium plus, as mentioned by Ted yesterday, is 8.6 10⁻18. So you see, we are entering now the 10⁻18. That corresponds to 10⁻18 corresponds to 10 centimeters. That shows you in particular that now to define the time, we can no longer define it on Earth, because you cannot determine where you are exactly on the gravitational potential. So the definition of time now in the future, I'm sure in a few decades, will be done in space. Of course, you could use also this effect to make geodesy, to determine what is called the geoid, the surface around the sun where the gravitational potential has a certain value. That would have a very interesting geophysical application. And that picture, obtained by the NIST Boulder Group, shows you also a very interesting fundamental question. Do fundamental constants are really constant? Do they vary in time? There are some theories which predict they vary in time. And in this experiment, we have been able to measure alpha, the time structural constant. It is minus 1.6 plus or minus 2.3 10 to minus 17 per year, which is still compatible to 0, but if the accuracy increases furthermore, perhaps we'll see something. That's a very important issue. Now I switch to the last application of the talk. 10 minutes more. 5, okay. That's the last anniversary, 1995. These three people, Eric Cornell, Wolfgang Ketterle, and Carl Wyman, were able to observe an effect which was predicted in 1924 by Einstein, but they were able to observe it in a gas, in a laser-cooled and gas with evaporation. And that's a great achievement. And a way of looking at this was a sketch on the picture of Science magazine. They represent the atoms which are condensed in the lowest quantum state of the trap which contains the gas as an army of soldiers marching in lockstep. All atoms are in phase and exactly like soldiers of an army in lockstep. What is fascinating in this experiment is that you have a million of atoms all in the same wave function having a microscopic size, 50 micron size. You have a macroscopic matter wave. This is a spectacular observation of matter wave. Of course, a lot of studies have been devoted to it since that time. Just a few words about them. If you take two condensates and you drop them, they overlap and they form a beautiful interference fringes. Interference between two matter waves, two macroscopic matter waves. If you have in a trap a condensate and if you make a small leak, a beam of current atomic waves come out in the same manner as the beam of current light waves come from a laser. So this is called an atom laser. If you try to put the condensate in a trap and if you rotate the trap, the matter wave does not rotate like a rigid body, it rotates like a quantum liquid, forming what is called quantized vortices. Example of them observed in the Jean Dalibard group at École Normale, and also in Wolfgang Ketterle group at MIT. And you see this hole here corresponds to what is called vortices. You have a vortices where the density of matter vanishes along the axis and where the system rotates around the axis with a velocity which is not increasing proportionally to the distance from the axis, but it decreases inversely proportionally to the distance. It's really a quantum system. And what is beautiful is that when you compare this picture to what is observed in a superconductor, Napri-Kozloff lattice, you find quite similarity. And that the main feature of this research field, you begin to observe with these ultra-cold quantum gases effects which up to now were only observed in liquid or solid, superfluid helium or superconductor. And the evolution of the research, the trend in this research field is that now people have acquired a full master of all degrees of freedom of the sample. They can control the position, the velocity, the speed, even the interaction between atoms with the so-called phase bar resonance, which I have no time to explain. And now people are more and more interested in situations where the atoms are strongly interacting, strongly correlating, and where one hopes to obtain answer to this problem, easily to obtain with this simple system because every parameter can be controlled, and we can get a better understanding of more complex situations observed in liquid like superfluid helium or in solid like high TC superconductor and so on. Okay, so I have no time to describe this kind of experiment. It will be too complicated. And I will just mention something which is beautiful. There is a very interesting discovery which has been made about 15 years ago, which is called Feshbach resonance, which is a way of using a knob for controlling atom-atom interaction. You can, by changing the magnetic field, realize a situation where the atoms of a gas are repelling, attracting each other, or not interacting at all. And using this Feshbach resonance, it is possible now to start with a pair of atoms and by scanning the magnetic field to produce an ultra-cold molecule. So the field of cold atoms now is moving from atoms to molecule. And now more and more groups are trying to observe ultra-cold molecule and to increase the complexity of the molecule and to achieve new situations. So I will switch to my conclusion now. I hope to have convinced you that the better understanding of light-matter interaction, which have been developed during the last few decades, allows now us to invent new light sources like laser light. Laser light is a beautiful application of basic research, and also invention of new schemes like optical pumping, laser cooling, for manipulating atoms. I think that these advances are opening new research fields, allow us to ask new questions, to investigate new systems, new states of matter, like Bose-Einstein condensate, which share common features with light waves. I think that the history of light and matter is very interesting because it provides a very clear example showing how basic research changed our vision of the world by introducing conceptual revolution, like relativity, quantum mechanics, and also leads to unexpected application, like the laser, the MRI, the transistor, and so on and so on. So, addressing to the young people in the audience, I think that this example shows you that science is a fascinating adventure which should attract you to enter in this field, excite you for exploring new fields, and also find, of course, new solutions for improving the mankind condition on Earth. Thank you very much for your attention.